We started working on this optimization problem in the last video, and we're here to finish it. So just a quick recap, we were describing this ring on a string, and we were trying to grapple with, okay, as we push and pull on this string here, it's going to trace out this curve, but what does that really mean? And we found that, as we push and pull on this ring here, it's constrained to this curve by the length of the string. So we found a length equation here, and we said that this function here, y of x, is defined implicitly in our length equation. And that's to say that, okay, as we push and pull on the string, we even drew this diagram. We're just going to have different right triangle setups. And that's because our function is defined implicitly by this length equation. So now we want to find, and we even made the argument, okay, we know that this is going to be a minimum point by just kind of looking at our diagram and saying, well, it's not going to occur at our endpoints, it's going to occur in between, and this looks like a minimum point. So we covered that. We looked at some of our endpoints, but now we have this information and we want to find something about this critical point here. So we want to look at when y prime is 0 and we have this length equation. So what we need to do now is find the derivative of this length equation with respect to x and then plug in when y prime is 0 and see what kind of information we get. So why don't you pause the video and work on that. All right, assuming that you've given it a go, let's take a derivative with respect to x. So on this left-hand side, again, this length is constant, so its derivative is 0. And then on this right-hand side, we're going to apply some chain rule. So we have 1/2 times x squared plus y squared to the negative 1/2 power. And then the derivative of the inside is going to be with respect to x. So this is 2x plus 2y times y prime. Again, some chain rule. So then that's the derivative of this guy. Again, just applying the chain rule. And now we have to take the derivative of this thing over here. So we have plus 1/2 times this whole thing. So we have a minus x squared plus b minus y squared, and then this is to the negative 1/2 power now. And now by the chain rule, we have to take the derivative of the inside, and we're going to end up applying more chain rule. So it's just an endless chain rule. So we have, what's the derivative of a minus x squared with respect to x? Well, it's going to be 2 times a minus x, and then the derivative of a minus x with respect to x is negative 1. This is times negative 1. And now, what's the derivative of b minus y squared? Well, that's going to be 2 times b minus y, and the derivative of b minus y with respect to x is going to be negative y prime. So this is negative y prime. So that is what we find our derivative to be. And this is a pretty lengthy derivative here, so let's try to simplify, and then we will want to plug in this condition here when y prime is 0. Give us some information about this critical point. So let's simplify, and it looks like we have a denominator here, so we can write that guy out first. So we have 2 times the square root of x squared plus y squared in our denominator, and then in our numerator, it looks like we can factor out a 2. So let's factor out 2, and we're left with x plus y times y prime. All right, so that's this whole first thing here. And now dealing with this second term here, we have plus, and again, we have a numerator and denominator. So in the denominator, we have 2 times a minus x squared plus b minus y squared. And then numerator, let's see here. It looks like we can factor out a 2, and we can factor out a negative 1. So let's factor out negative 2. Let's factor out negative 2. And we're left with a minus x plus a b minus y times y prime. So plus b minus y times y prime. And that is all in our numerator. So now this is again equal to 0, and now we want to specifically look at this critical point. So we want to know what happens when y prime is 0. So we're just going to plug in when y prime is 0 and see what we get. These 2's are going to cancel, and this y prime times something is just going to be 0. And these twos are going to cancel, but we can't forget the negative. We cannot forget the negative. So, and then again, when we plug in 0 over here, this is going to go to 0. So we're left with this. 0 is equal to x over the square root of x squared plus y squared. And then plus, well, we have this negative. So this is actually going to be negative 1 times a minus x over the square root of a minus x squared plus b minus y squared. Okay, so simplify. This is simplified, and we have plugged in the condition when y prime is 0. So this is what we're left with. This is what we got. What is this saying? And you might be like, what is this saying? Well, we need to go back up to our graph and see if anything is revealed by our graph. We're looking, what is x over the square root of x squared plus y squared? What is that? What is that? Well, here's x. Here's a square root of x squared plus y squared. And what I really want you to see is if we call this angle here, if we call this angle alpha, well then sine of alpha is x over the square root of x squared plus y squared. So down here, let's go back down and rewrite it like that. This is really the sine of alpha. The sine of alpha is this. And now, what is this guy over here? What is a minus x over the square root of all of this? Well, let's see. Ooh, jumped up. Here we go. So what is all of that? What is a minus x over the square root of all of this? Well, again, if we were to call this angle, we can name it, let's say beta. If we were to call it beta, well, then this is the sine of beta. So that's the sine of beta. So we have minus, we can't forget this negative here, minus the sine of beta. Minus the sine of beta. And again, all of this is 0. So then solving for this, we find what? We find that alpha is equal to beta. Alpha is equal to beta. Alpha is equal to beta. And that is some pretty interesting answer. Because what is this saying? This is saying that, okay, hey, for any string setup here where we're hanging a ring on it, say it's something like this even, and we were to hang a ring on it with something like that, that what this is saying, where this ring is going to settle, even in this string setup, for any string setup, that this ring is going to settle and have the property, this point is going to have the property that if you were making a vertical, that is not a good vertical. Let's try again. If you were making a vertical like that, the angles between this vertical and the string, they're going to match. They're going to have the same angle. Here, we'll call this one yellow. This one will be alpha, and this one will be beta. That these angles are going to be the same, and that could be for any string setup. You hold the string anywhere else. These angles are going to be equal. That's what this answer is saying, and that's pretty cool. And you might say, well, okay, that's telling me something about the angles, but what about the point? And you can solve for x and y, and it would be you'd get a longer expression. But really, this is a more interesting answer because you're getting this property that, hey, this point down here, wherever it settles, has this property that these angles are going to be equal, which is pretty cool. And if you want to find x and y, maybe we'll throw that in an article and help you calculate those out.